Let's get started with probability distributions. A probability distribution describes how probabilities are distributed over the values of a random variable. Think of it as a mathematical way to tell us which outcomes are likely and which are rare. Why do distributions matter in AI and ML? First, every ML algorithm makes distributional assumptions about data. Second, they help us quantify uncertainty in predictions. Third, generative models like GANs and VAEs rely heavily on distributions. And finally, all statistical testing and A/B testing use distributional theory. There are two main types of distributions. Discrete distributions handle countable outcomes like integers or categories using something called a probability mass function. Continuous distributions handle infinite possible values using a probability density function. The key difference? Discrete is like counting individual items, while continuous is like measuring on a scale. Throughout this video, we'll explore 14 essential distributions, from uniform and binomial for discrete data to normal, exponential, and gamma for continuous data. We'll also cover specialized distributions like beta for probabilities, chi-square for testing, and students t for small samples. Let's dive in. Let's start with the discrete uniform distribution, also known as the fairness distribution. The formula is simple. P of x equals x is 1 over n. This means each of the n outcomes has exactly equal probability. Imagine rolling a fair six-sided die. Each face has a 1 in 6 chance of appearing. Here's what equal probability looks like visually. When we roll a fair die, each outcome from 1 to 6 has the exact same probability of 1/6. Notice how all the bars have identical height? That's the hallmark of a uniform distribution, complete fairness with no outcome favored over another. In machine learning, we use discrete uniform distributions everywhere. For random initialization, we assign weights uniformly to avoid bias. Baseline models assume uniform distribution over all classes for random guessing. Data augmentation randomly selects transformations with equal probability. And Monte Carlo methods generate uniform random samples for simulation. The key takeaway? The discrete uniform distribution represents complete fairness. No outcome is favored over another. For a six-sided die, the mean is 3.5, right in the middle. This distribution is your go-to whenever you need pure randomness with no bias. The binomial distribution answers one key question: how many successes in n tries? The formula involves combinations, where n is the number of trials, p is the probability of success, and k is the number of successes we're counting. Here, we see 10 coin flips resulting in 6 heads out of 10. Binomial has two key parameters. First, n represents the number of independent experiments, in our example, 10 coin flips. Second, p is the probability of success on each trial, 0.5 for a fair coin. The crucial requirement? Each trial must be independent with the same probability p. Look at the distribution shape for 10 flips with p equals 0.5. It's symmetric and bell-shaped, peaking at 5 heads. The probability decreases as we move away from the center. When p equals 0.5, we get this beautiful symmetry, but when p is not 0.5, the distribution becomes skewed. Binomial distributions are everywhere in machine learning. Use them for binary classification to model positive predictions. A/B testing relies on binomial to compare conversion rates. Quality control calculates defect probabilities. And dropout in neural networks? That's Bernoulli sampling, which is just binomial with n equals 1. The key takeaway? Binomial answers how many successes in repeated binary trials. The Poisson distribution asks how many events in a time window. The formula uses lambda, the average rate of events per interval, combined with e to the negative lambda. Watch these events occur randomly over time. They're unpredictable individually, but follow a pattern overall. Here's what Poisson looks like with lambda equals 3. The distribution is right-skewed. peaking near the average of 3 events. Notice the long tail to the right? That's characteristic of Poisson. The peak occurs near lambda, with decreasing probability as we move away. How does Poisson differ from binomial? Binomial has a fixed number of trials, like 10 coin flips. Poisson has unlimited possible events in a fixed time or space, like customers per hour. Mathematically, Poisson is the limit of binomial when n approaches infinity and p approaches 0, with n times p equals lambda. Poisson is crucial in machine learning. Use it for anomaly detection to spot unusual event rates, like network intrusions. In NLP, it models rare word occurrences. Time series forecasting predicts count data, like website visits. Recommendation systems model user interaction counts. The key takeaway: Poisson models rare events occurring randomly over time or space. The multinomial distribution is binomial's multi-category sibling. Instead of just success or failure, we now have k different categories. The formula extends binomial to handle multiple outcomes simultaneously. Think of rolling a die 8 times. We're tracking how many times each face appears. Let's see an example with 30 die rolls. Face 1 appeared 5 times, face 2 4 times, face 3 6 times, and so on. Each category has probability p equals 1/6. Notice how all the counts sum to 30? That's a key property. The sum of all category counts must equal the total number of trials. How does multinomial compare to binomial? Binomial handles just 2 categories, success versus failure, heads versus tails. Multinomial generalizes this to k categories, like die faces 1 through 6, or multiple classes in classification. When k equals 2, multinomial reduces back to binomial. Multinomial is essential for multi-class classification, modeling probability distributions over k classes. Topic modeling with LDA uses multinomial for word distributions. Neural network softmax outputs are multinomial probabilities, and categorical data analysis relies on multinomial for survey responses and user preferences. The key takeaway: multinomial handles multiple categories simultaneously. The continuous uniform distribution is the flat distribution. The probability density function is simply 1 over b minus a for values between a and b. This creates a perfect rectangle, equal probability density across the entire interval. It represents complete uncertainty within a bounded range. Watch these random points appear uniformly across the interval from 0 to 1. Notice how they spread evenly. There's no clustering, no preference for any region. Every value is equally likely. This is what pure randomness looks like in continuous space. The continuous uniform has simple properties. The mean is the midpoint, a plus b over 2. The variance is b minus a squared over 12. It increases with the interval width. This is the maximum entropy distribution for bounded continuous data, meaning it represents the most uncertainty possible. In machine learning, continuous uniform is fundamental. It's the basis for random number generation using inverse transform sampling. Neural networks use uniform initialization for weights, like Xavier or Glorot initialization. Bayesian inference uses it as a non-informative prior. And data augmentation randomly selects crop positions, rotation angles, and brightness adjustments. The key takeaway: uniform represents complete uncertainty over a continuous range. The normal or Gaussian distribution is the king of distributions. This famous bell curve is defined by 2 parameters: mu for the mean, which centers the distribution, and sigma for standard deviation, which controls the spread. It appears everywhere in statistics and machine learning. Let's understand the 2 key parameters. Mu, the mean, determines where the center of the curve sits, shifting it left or right. Sigma, the standard deviation, controls the width. Larger sigma means more spread out, smaller sigma means more concentrated. Together, they completely define the shape. Here's the famous 68-95-99.7 rule. 68% of data falls within plus or minus 1 sigma of the mean, 95% within plus or minus 2 sigma, and 99.7% within plus or minus 3 sigma. This rule makes the normal distribution incredibly useful for understanding data spread and detecting outliers. Why does normal distribution dominate machine learning? The central limit theorem says sums of many random variables tend toward normal. It's the foundation of statistical inference. We use it for weight initialization in neural networks, adding Gaussian noise for regularization, and modeling latent spaces in GANs and VAEs. The key takeaway: normal distribution appears everywhere thanks to the central limit theorem. The exponential distribution answers one key question: how long until the next event? The formula uses lambda e to the negative lambda x, where lambda is the rate parameter, representing events per unit time. Watch this decay curve. It starts high and drops off exponentially. The most unique feature of exponential is the memoryless property. The probability of waiting an additional t time units is the same regardless of how long you've already waited. For example, if a customer hasn't arrived in 5 minutes, the probability they arrive in the next 2 minutes is the same as if you just started waiting. How does exponential differ from Poisson? Poisson is discrete and counts the number of events. Exponential is continuous and measures time between events. If events follow a Poisson process with rate lambda, then the time between events follows an exponential distribution with the same lambda. Exponential is crucial in machine learning. Use it for survival analysis to model time until failure or customer churn. Queue modeling uses it for service time distributions and network packet inter-arrival times. Reliability engineering predicts hardware failures. And in reinforcement learning, it models time between state transitions in continuous time Markov processes. The key takeaway: exponential models waiting times and is the only memoryless continuous distribution. The log-normal distribution is normal's positive-only skewed cousin. If the logarithm of x follows a normal distribution, then x follows a log-normal distribution. Notice this right-skewed shape. It's always positive and has a long tail to the right. The key is the log transformation. On the left, we have x following a log-normal distribution, right-skewed with positive values only, like stock prices or incomes. Take the logarithm, and on the right, log of x follows a symmetric normal distribution. This transformation makes skewed data much easier to analyze. Log normal has 4 key properties. First, it's always positive, perfect for modeling prices, sizes, and durations. Second, it's right-skewed with mode less than median less than mean. Third, it arises from multiplicative processes like compound interest. And fourth, it has heavier tails than normal, capturing more extreme values. In machine learning, log normal is essential. Stock prices and returns follow log normal because prices can't be negative and grow multiplicatively. Income distributions and household salaries are right-skewed with positive values. File sizes and network traffic follow multiplicative processes with heavy tails. And in latent variable models like VAEs, we use log normal when the log of a latent variable is normally distributed. The key takeaway: use log normal for positive, skewed data from multiplicative processes. The gamma distribution generalizes the exponential distribution. It's defined by 2 parameters, k for shape and theta for scale. The formula involves x to the k minus 1 times e to the negative x over theta. Gamma is actually equivalent to gamma distribution with specific parameters. Gamma has 2 key parameters that give it incredible flexibility. The shape parameter, k, controls the shape of the distribution. When k equals 1, it becomes exponential. The scale parameter, theta, stretches or compresses the distribution. Larger theta means more spread out. Different k values create vastly different shapes. Gamma has important family connections. When k equals 1, gamma becomes exponential. When k equals nu over 2 and theta equals 2, it becomes chi squared. And here's something cool. The sum of k independent exponential random variables follows a gamma distribution. Gamma is a generalization that unifies several important distributions. In machine learning, gamma is versatile. It's the conjugate prior for Poisson rate parameters and exponential scale parameters in Bayesian inference. It models wait times until k events occur, generalizing exponential for a single event. In insurance and finance, it models claim amounts and loss distributions. And in variational inference, it approximates posterior distributions in Bayesian deep learning. The key takeaway? Gamma is the flexible distribution for positive continuous data. The beta distribution is the probabilities of probabilities distribution. It's defined on the interval from 0 to 1 with parameters alpha and beta. The formula involves x to the alpha minus 1 times 1 minus x to the beta minus 1. Beta distribution models probabilities themselves, perfect for values between 0 and 1. Beta is incredibly shape-shifting with alpha and beta. When alpha equals beta equals 1, it's uniform, all probabilities equally likely. When both are less than 1, you get a U-shape favoring extreme values near 0 or 1. When both are greater than 1, you get a bell shape concentrated around the mean. And when alpha doesn't equal beta, the distribution becomes skewed, favoring one side. Beta is a Bayesian inference superstar. Start with a prior beta distribution with parameters alpha and beta, your initial belief about probability. After observing S successes and F failures, update to a posterior beta with parameters alpha plus S and beta plus F. This is called a conjugate prior. The posterior stays in the same family as the prior, making calculations elegant. In machine learning, beta is essential. Use it for Bayesian A/B testing to model conversion rates and compare posteriors to determine the winner. Thomson sampling from multi-armed bandits uses beta distributions for exploration versus exploitation. It models any probability constrained to 0 to 1, like click-through rates and success probabilities. And beta generalizes to directly distribution for modeling probability vectors and topic modeling. The key takeaway, beta models probabilities and is essential for Bayesian inference. The Weibull distribution is the failure analysis distribution. It's defined by shape parameter k and scale parameter lambda. The formula combines these to create a flexible distribution for modeling time to failure. Weibull is essential in reliability engineering. The shape parameter k determines the failure behavior. When k is less than 1, you get decreasing hazard. Failure rate decreases over time like infant mortality. When k equals 1, it becomes exponential with constant hazard, random failures. When k is greater than 1, you get increasing hazard as things wear out from aging and fatigue. And when k is around 3.5, it approximates a normal distribution. The bathtub curve describes product life cycle failure rates. In early life, with k less than 1, you have high initial failures from manufacturing defects. During useful life, with k equals 1, you have constant low failure rates from random failures. In the wear-out phase, with k greater than 1, you have increasing failures as components age. In machine learning, Weibull is crucial for reliability engineering, predicting hardware failures, scheduling preventative maintenance, and optimizing replacement policies. Survival analysis uses it to model time-to-event data like customer churn, patient survival, and equipment lifetime. Quality control analyzes product lifetimes, warranty claims, and failure patterns. And it's related to extreme value distributions for modeling rare events and outliers. The key takeaway? Weibull's flexibility makes it the go-to for failure analysis. The chi-square distribution is the hypothesis-testing workhorse. Chi-square with n degrees of freedom is actually a gamma distribution with specific parameters. Here's how it's constructed. If you take n independent standard normal random variables, square each one, and sum them up, you get a chi-square distribution with n degrees of freedom. The shape of chi-square depends entirely on degrees of freedom. With n equals 1, it's highly right-skewed starting at 0. With n equals 2, it becomes an exponential distribution. As n increases, the distribution becomes more symmetric and approaches normal. The mean equals n, and variance equals 2n. Chi-square is used in 4 common statistical tests. The goodness of fit test asks, does data match an expected distribution? The independence test checks if 2 categorical variables are independent. The variance test determines if population variance equals a specific value, and the homogeneity test checks if different populations have the same distribution. In machine learning, chi-square is essential. Use it for feature selection with the chi-square test for independence between features and target in classification. Categorical data analysis tests relationships between categorical variables using contingency tables. Model evaluation uses goodness of fit tests for probabilistic models and distribution matching, and variance estimation creates confidence intervals for variance in regression and ANOVA applications. The key takeaway? Chi-square is essential for statistical testing in ML pipelines. Student's t-distribution is normal's cautious little brother. The formula is t equals x bar minus mu over s divided by square root of n, with nu equals n minus 1 degrees of freedom. The t-distribution accounts for uncertainty when estimating population variance from small samples. How does t-distribution compare to normal? Normal assumes known population variance, has thinner tails, works for large samples over 30, and is more confident. Student assumes unknown population variance, has heavier tails, works for small samples under 30, and is more cautious. As degrees of freedom approach infinity, t-distribution converges to the normal. Student has 4 key properties. First, heavier tails mean more probability in extreme values, accounting for small sample uncertainty. Second, it's symmetric and bell-shaped, centered at 0, like normal. Third, lower degrees of freedom means heavier tails, while higher degrees of freedom means closer to normal. And fourth, it's more robust and less sensitive to outliers than normal in small samples. In machine learning, t-distribution is crucial. Use it for small sample inference with confidence intervals and hypothesis tests when sample size is under 30. A/B testing compares means between 2 groups with limited data using t-tests. Robust regression uses t-distribution for error terms to make regression less sensitive to outliers, and Bayesian modeling uses priors or likelihoods with heavy tails for robustness in probabilistic models. The key takeaway: use t-distribution for small samples or when you need robustness. Welcome to the family tree of probability distributions. Distributions aren't isolated. They're connected through special cases, limits, and transformations. Understanding these relationships helps you choose the right distribution for your problem. Let's look at special cases and parameter settings. Binomial with n equals 1 becomes Bernoulli, just a single trial. Multinomial with k equals 2 reduces to binomial, only 2 categories. Gamma with k equals 1 becomes exponential, the shape parameter of 1. Gamma with k equals nu over 2 and theta equals 2 becomes chi-squared. Beta with alpha equals beta equals 1 becomes uniform on 0 to 1. And Weibull with k equals 1 becomes exponential. Now for limiting relationships. As n approaches infinity, binomial approaches normal with mean np and variance np times 1 minus p. As lambda approaches infinity, Poisson approaches normal with mean and variance both equal to lambda. Binomial approaches Poisson when n approaches infinity and p approaches 0 with np equals lambda constant. And as degrees of freedom approach infinity, t-distribution approaches standard normal. The central limit theorem says the sum of many random variables approaches normal. Finally, transformations connect distributions. If x follows log normal, then log of x follows normal, the log transformation. The sum of k-squared standard normals follows chi-squared with k degrees of freedom, squaring normals. And the sum of k-independent exponentials with rate lambda follows gamma with k and 1 over lambda, summing exponentials. The key takeaway: understanding relationships helps you choose the right distribution. Which distribution should you use? Let's walk through a decision flowchart. First, is your data discrete or continuous? If discrete, consider binomial, Poisson, multinomial, or discrete uniform. If continuous, consider normal, exponential, gamma, beta, Weibull, or log normal. Second, what's the range? If it's 0 to 1, use beta. If it's positive only, use gamma, Weibull, or log normal. If it can be any value, use normal or t. Third, what are you modeling? For counts, use Poisson. For success or failure, use binomial. For wait times, use exponential. Here's a quick reference cheat sheet for all distributions. Uniform for equal probability and randomization, binomial for fixed trials with binary outcomes, Poisson for event counts in intervals, normal for symmetric data where central limit theorem applies, exponential for time between events, log normal for positive right-skewed data, gamma for flexible positive continuous data, beta for probabilities and values in 0 to 1, Weibull for failure analysis and reliability, chi-square for hypothesis testing and variance, students t for small samples and robustness, and multinomial for multi-category outcomes. You've mastered distributions. Remember 4 key points. First, understand your data type, discrete or continuous. Second, know the range and constraints. Third, match the distribution to the problem. And fourth, use relationships to simplify. Now go build amazing machine learning models.